and computed two loop contributions and so that it vanishes. But the explanation is trivial. It's just this Spurian analysis argument. Okay.
I'm sorry?
So there is this conjecture which can be proven for every Lagrangian field theory. I don't know how to prove it beyond, but it's up for grabs. I think it's a very important result.
Taking the high temperature limit first?
What's the question?
Do you need to take the high temperature limit for the conjecture?
So this two-point function is a function of momentum and temperature. So what I'm talking about is just the leading order contribution in the expansion in momentum over temperature. So there are some corrections of the, of the order of momentum over temperature. This is the leading result. So the conjecture is about the leading result in the expansion in momentum over temperature.
So the question is, when you evolve into the zero coupling limit, say asymptotic freedom, then maybe at that high energy scale, the temperature effect, the radius can be resolved in this scale. So the high temperature limit is...
Look, the only thing that you're assuming here, so if you take some quantum filter at non-zero temperature, then there will be typically a gap, which is of the order of the temperature. Now you can change the coupling constants, but it won't bring any states to zero mass, generically. So the effective field theory approach would be valid throughout this limit. Because you just change, you change the coupling constants, but the fact that the gap is of the order of the temperature would usually be expected to remain true. So this is why this argument makes sense.
So the gap also depends on the coupling.
The gap? Yeah, it may depend on the couplings, but as long as it's non-zero, the discussion makes sense. As long as there are no massless states that you hit on the way to free field theory. So if you can do this while avoiding massless particles, which is usually the case, then this argument would make sense. Okay, so there is no, I think it would be very important for somebody to explain why this is true, but beyond Lagrangian field theories, I don't know how to do that. But let's assume it's true, because it's true for Lagrangian field theories, and we'll see what are the consequences for supersymmetric theories. So now the problem is that instead of looking at a generic conformal field theory, I would like to consider supersymmetric quantum field theories. So we have this object A wedge dA, and it's fixed by trace of U1 over, let's say, 48 pi. So we have this interesting term in the Lagrangian. But now, if the theory is supersymmetric, we need to supersymmetrize this local action. Now we have to also specify what do we mean by A. Which global symmetry are we talking about? So one natural global symmetry in supersymmetric theories of the type that we discussed in the beginning is the R symmetry. So from now on, this global symmetry would be just the R symmetry for me. And then this trace U1 is the trace of the U1R anomaly in the four-dimensional supersymmetric field theory. So you need to supersymmetrize this Chern-Simons term. It turns out that it can be supersymmetrized by adding the Einstein-Hilbert term. So this is just the Ricci scalar. And another term, which is called H squared. And that's more or less it in some convention. So this is n equals 2. 3D supergravity computation. So if you look at the literature on n equals 2 3D supergravity, you will see that the Einstein-Hilbert term, when supersymmetrized, naturally contains this Chern-Simons term. And that's a established result in supergravity in 3 dimensions. So it appears that if you accept the fact that this has a universal coefficient, in supersymmetric theories, it has far-reaching consequences. It means that also the coefficient of the Einstein-Hilbert term is independent of the coupling constants. And it's completely universally fixed by an anomaly. Okay, so this is not true in non-supersymmetric theories because they're not related by any symmetry. But in supersymmetric theories, the Einstein-Hilbert term appears to be related by symmetry to this Chern-Simons term. So if this is fixed, then this is fixed. Now what is H? This is just a field in the 3D supergravity multiplet, which is explicitly known. So I won't write a formula for it, we don't need it, but it's in the notes actually. This is explicitly known for all the manifolds of the type Seifert times S1. And this is Seifert. So we know we have a completely closed formula for what this is on any manifold of this type. The Ricci scalar is very easy to evaluate. Once you are given the metric, you just evaluate the Ricci scalar. And this we also know on for every manifold of this type.
H is what type? Is it scalar?
Yes, it's a scalar. So this is like this is the flux of some form through M3. So it's a scalar flux, and it's known explicitly on every manifold of this sort. So you see that once you add supersymmetry to the story, then there is an interesting consequence, which is that now the integral of this over the 3 manifold is in most cases non-zero, because the Ricci scalar is non-zero and this is non-zero, while this may be zero in many interesting cases. These guys are non-zero. So that implies something universal about the high temperature limit of supersymmetric partition functions.
If you didn't have supersymmetry, there would be another term, namely this postulate.
Yes. I've,
Yes.
yes. Yeah, another fact that I've glossed over because I don't have time to explain is that indeed this is the leading term in the expansion at high temperatures in supersymmetric filters, because the cosmological constant cannot be supersymmetrized, as you very well know. Supersymmetry predicts that the cosmological constant is zero. So the cosmological term is absent, and the Einstein-Hilbert term is actually the dominant term at high temperatures. Therefore, one has a prediction for the partition function on every Seifert manifold times S1 in the limit that beta goes to zero. It just comes from that. And the answer is going to be always, so this is, let's take the logarithm of the partition function for simplicity. The answer is going to be trace of the U1R symmetry times some length scale. This length scale is set by integrating this term over the Seifert manifold. It depends on the specific manifold that you are studying, over beta, up to some prefactor that is universal. And this length scale can be computed on every given Seifert manifold, in particular on S3 times S1, where it's just R, the radius of the S3. And the last piece of information that I need to provide you with is that in superconformal filters, the trace of the U1R anomaly, which appears in that formula, is proportional to A minus C, where A and C are the central charges. So that is more or less, these are more or less all the ingredients that one needs to prove that the log of the partition function on S3 times S1 in the limit that the temperature goes to infinity is given by A minus C over beta. And this is normalized by the radius of the S3, which you can take to be 1. Okay, so this is the Hardy formula in 4-dimensional SCFTs. And you see that basically it relies on some resultant thermal filter that one can prove for all Lagrangian filters, but still evades a non-perturbative proof. And it relies on the supersymmetrization of that general result in hydrodynamics. It relies on supersymmetrizing using 3-dimensional n equals to supergravity. And once these ingredients are in place, this follows immediately. Now there are two consequences that I want to discuss. How much more do I have? Okay. I want to discuss two consequences of this result. Are there any questions? Yes?
Can I apply your argument G1R filter versus
Say again?
Can I apply your argument G1R filter emergent, which is not visible?
Oh. Well, this is true for any SCFT. Okay? So this is true in any SCFT for the superconformal R symmetry. This is true in any SCFT when the U1 R symmetry is the right one. And this result is no, but it doesn't matter because you see this object has a combinatorial interpretation as a sum over operators using the right superconformal R symmetry. And so this result is just always true.
Well, sometimes when you calculate local coupling index, you already assume there's a normal U1.
This result is always true. Now, whether you can compute the left-hand side explicitly using localization is a different issue. So there are two different issues. One is, can you compute the left-hand side explicitly using localization and check if this is true?
Yeah, I don't care about
for you to be able to carry out this exercise, you need to know the R symmetry along the RG flow. But whether or not you can do that, this result is true. It's going to be true. It's just it may be hard to verify in some examples, but
when you try to prove this result, k is equal to 1 over 12 U1, you assume that you compute it from the free-forming theory, right?
yes,
Where you can see this U1 symmetry.
yes.
But if this U1 symmetry is not visible in the B theory, then how can you say
You see, what you're asking. So what you're asking is the following. So suppose there is a CFT, which is this has nothing to do with supersymmetry, right? So you're saying that there is some CFT with a U1 symmetry, and then there is free field theory. And you're saying suppose that there is no way to connect this CFT with free field theory while preserving the U1 symmetry. That's what you're asking. Now, in the context of supersymmetry, there are various issues, and it may be hard. You may be able to find examples where it's not possible to connect it to a free field theory with the same U1. But if you think about it in general, having nothing to do with supersymmetry, it's extremely unlikely that this would be the case, because this is something that, if you study just there may be emergent U1 symmetries in some CFTs, but so for them, this argument would not apply unless there is a way to UV complete the theory preserving these U1 symmetries. This, in general, should not be too hard in the absence of supersymmetry, I would think. It would be hard to prove a theorem that some U1 symmetry cannot be preserved by, say, a lattice or some UV completion. So, in principle, if the theory is so in this sense, you could say that this U1 is non-Lagrangian. If such a theory existed, you would say that this U1 is non-Lagrangian, and it would fall under the class of models for which I cannot prove anything. But these examples that you had in mind, where the R symmetry does not follow from the RG flow, are actually completely fine. Because it's just that because you insist on supersymmetry. Okay, so.
I think I missed the essential point in the logic. How do you manage to relate the index commutation to thermal boundary?
Yes, so I skipped one technical issue, which is that on the one hand, this conjecture has been made in the context of thermal field theory. So to make this conjecture, it was important to assume that there is a gap. Now, if the boundary conditions are periodic, there is no gap in general, because you reduce, you get the massless field theory. But in fact, this particular term doesn't get affected in the generating function. And the reason is the following. This term is proportional to the temperature. It's 1 over beta if you put the dimensions back in. You see? It's something that diverges when the temperature goes to infinity. So a bunch of massless particles cannot contaminate the partition function with something that goes to infinity when the temperature goes to infinity. They would contribute something of order 1 to the partition function on S3. So when you reduce, you get infinitely many fields on S3. This comes from integrating out the infinitely many KK modes. But the massless particles on S3 cannot modify this result, because they themselves would just contribute something finite on S3. So they won't mix up with the contribution from integrating out infinitely many KK modes. So this particular technical point can be elaborated, but it doesn't matter in the end because of this story. Okay, so the 2 comments that I want to make. Any more questions? So the two comments that I wanted to make, and then I'll make a short introduction to the next topic. So comment number one is that usually A and C, which are the central charges of the theory, they're computed from flat space, zero temperature, 3-point functions. That's the way these objects are usually introduced in quantum field theory. These are the central charges in four-dimensional CFTs. Here you see that at least in supersymmetric theories, at least the difference, A minus C, can be completely extracted just from the BPS spectrum. You don't need to study 3-point functions. So at least A minus C can be completely extracted from the spectrum of BPS operators, from the spectrum of operators or BPS operators. Okay, so this is an amusing point. The disadvantage can be, once you know the BPS spectrum, you know the difference between the anomalies. You don't need to study 3-point functions of the energy momentum tensor multiplex. The second comment is that there is a crucial issue with the sign. So you see that the sign matters a lot. So let me just get the sign straight. So this minus A minus C. So this is the correct sign. So if A is bigger than, if A is smaller than C, so we have three cases. A smaller than C, A equals to C, and A bigger than C. And they all seem very different from this point of view. So if A is smaller than C, this is a positive thing in the limit of small beta. And we have infinitely many, we have a proliferation of BPS states at high dimension. So proliferation of BPS states, of BPS operators at high dimension. What do I mean by proliferation? So when the temperature goes to infinity, this statistical sum that sits on the left-hand side, something like e to the minus beta delta plus r, half r. So when beta goes to 0, all the BPS operators contribute more or less with the same weight, which is 1. So the final answer is dependent on how many BPS operators which are bosonic minus how many BPS operators which are fermionic you've got in the theory. Now, in general, you have infinity minus infinity, and in general, you expect that the answer would be infinity, meaning that there are infinitely many BPS operators which are bosonic, then infinitely many BPS operators which are fermionic, and there needs to be no relation between them. So in general, you don't expect any cancellations, and you get the proliferation of BPS states of high dimension, and this is what you get if A is smaller than C. When A is equal to C, there is a delicate balance that you get infinity minus infinity, which is equal to a finite number. Okay, because then the leading term cancels out. So that means that you have infinitely many BPS operators which are bosonic minus infinitely many BPS operators which are fermionic, and somehow they conspired to leave behind just a finite number. And here you get something which is even more unlikely, that somehow the BPS operators conspire so that they essentially cancel each other completely, even though there is no reason for that a priori. Indeed, most of the field theories that we know are here. It's extremely hard to construct quantum field theories in this class. Here we've got n equals 4. Okay, so in n equals 4 there is this delicate balance, and presumably you could have proven from this approach that this must have been the case because the Einstein-Hilbert term is not invariant under n equals 4 supersymmetry. It's only invariant under n equals 2 supersymmetry. So presumably there is a proof that A must be equal to C in n equals 4 field theories in this way, that you could just prove that the Einstein-Hilbert term cannot be this Chern-Simons term cannot be supersymmetrized in supersymmetric theories with 4 supercharges, and therefore A must be equal to C. And this is very, very rare. So it's extremely hard to construct quantum field theories in this class. And from this point of view, it's kind of intuitive, because the theories seems very non-generic, that infinitely many BPS states of one kind would cancel infinitely many of another kind. There is no relation between them a priori. And so this may or may not explain why it's so hard to come up with field theories in this class. Well, most of the examples that you could imagine sit in this class.
And is it
case the n equals 4 theory, the 1 by beta is replaced by log beta?
Oh, you're asking about the higher order terms. Now, I don't see why there should be a log beta.
Just to give the explicit answer. We know the explicit answer to this.
Yes, let me just recall what. Let me recall if it's replaced by log beta or order 1. Yeah, I think you're right. It's going to be log of beta multiplied by the dimension of the moduli space. And so, yeah, in n equals 4, presumably there would be log beta, and the coefficient here would be just the dimension of the moduli space of the theory on the circle. It would come just from non-compact scalars in 3 dimensions, which have no curvature coupling. And then there would be some order 1 term. So presumably this is the next term in n equals 4. Okay, so this is the story with this Cardi formula in 4 dimensions. In the remaining 2 minutes, I just want to explain what we're going to do next time. You can read about it maybe if you have time.
One more question, please.
Yes.
You said the question of whether something like this might hold for the actual partition function without supersymmetry is open.
So it's not.
I understood you guys at the beginning.
So we know several things. One is that the partition function depends on coupling constants without supersymmetry. Therefore, it cannot be fixed by a simple formula that involves only anomalies. But this is about the leading term, about the free energy term. Now, in general, the partition function also without supersymmetry has subleading terms.
Right.
And some of them, it's not inconceivable that some of them are fixed by anomalies. For example, because there is the conformal anomalies have some consequences for this three-dimensional effective action.
Some aspect of the partition function is fixed, but not the leading high temperature.
The leading high temperature thing is not fixed by anomalies, that's for sure. We know that from the 3 quarters. But subleading terms can be presumably fixed by anomalies. Okay. Are there any questions about that before I give a 1 minute or 2 minutes long introduction to the next topic? Okay. So the next topic is completely unrelated, but it's also an exercise in RG flows and quantum field theory and stuff like that. So the problem is the following. I'll just give the physical motivation. You can read about it a bit maybe before tomorrow, and then we quit. So suppose you're in 3-dimensional space. Okay, so you're in 3-dimensional space, and there is a bunch of spins. And you have the Ising Hamiltonian. Let's say that the energy is just, let's say S sigma I sigma j. And this is over nearest neighbors plus the magnetic field. Okay, so you have the Ising Hamiltonian for 3-dimensional this 3-dimensional Ising model, and you know that if you tune the temperature to be the critical temperature, this is described by the CFT, which is called the 3D Ising model. It's a continuum conformal field theory, and it has various critical exponents, and there is infinite correlation lengths, and so on and so forth. This is the usual second-order phase transition. So what's the problem that we want to study in the next time? Next time, the physical problem that we want to study is what happens if the couplings between the spins and the magnetic field are not actually known. So instead of considering one quantum field theory, one studies an ensemble of quantum field theories. And one tries to see if there is still infinite correlation lengths, or if you reach, if there is still a second-order phase transition. So experimentally, this kind of problem arises when you try to, for example, to realize experimentally the 3D Ising model phase transition, but you don't have a complete control over the magnetic field in the environment. So it's fluctuating a little bit. And the physical question that arises in that context is whether, even in the presence of some coupling constants that are fluctuating, would you still get a phase transition? Okay, so the actual problem is that suppose the magnetic field is still 0 on average, but it's fluctuating. So there is some thing like that. Okay. So we're studying quantum field theory where the coupling constant of some term in the action is not fixed, but it's stochastic. And we need to average over many quantum field theories and see if the conformal symmetry or if the critical behavior still survives. So that's a problem in studying the space of theories. some sense, right? And I'll define the problem more carefully next time. But the central question is what happens when you start to average over quantum filters? Can you still get a conformal fixed point, a fixed point of the renormalization group, and stuff like that? So you can read about it a little bit before. Are there any questions? That's more or less it.
Last, you talked about four-dimensional data and three-dimensional Chern-Simons, and you showed that the kappa is observable. So I'm interested in whether there is any possibility of measuring kappa experimentally. And Chern-Simon theory appears in the description of quantum Core effect.
Yes, exactly.
But it is relatively low temperature, and you are talking about the high temperature, but still I wonder whether there is any possibility of measuring.
Yeah, I think there is. So physically, this Chern-Simons term corresponds to the fact that if there is some vorticity in the fluid, it creates a current in the perpendicular direction. So it's like a vertical magnetic effect. And I believe it's in principle measurable.
Other questions? So if not, let's thank Zohar.
So there's a quick announcement about transportation to the dinner place.